Thanks, Sophie. So, hello everyone. I'm Asaad Kaadan. I came today from Seattle to talk about Modular Electronics and my upcoming project, Hexabit. This is the first ever public presentation about the project. It's really very early bird, so I'm very excited about it. Thank you all for being here. And thanks, Sophie, for inviting me. Cool. So, is it working? Yeah. So, I'm gonna talk briefly about why are we here today, talk about Hexabit's concept. My journey so far in the world of modular electronics hasn't been straightforward. It was convoluted as usual. What's the difference between Hexabits and everything else out there, and state of the project, show some video examples, and at the end we have some hands-on demo. If you would like to smell some solder fumes. So a bit of background about myself. I have Bachelor in Electronics, University of Aleppo, both Masters and PhD from University of Oklahoma. I worked with some agencies like NASA, German Aerospace Center, and Oklahoma Department of Transportation on topics like optical wireless communication, drones, IoT. Right now I'm embedded robotics engineer in Seattle with a company called Free Fly Systems. We build robotic platforms for movie makers, Hollywood guys, and actually we just launched product yesterday. So build all kinds of drones, stabilized gimbals, and platforms that are used by professional camera makers. So boring stuff. This is the only boring slide. How many people in this room ever thought or actively pursued a modular electronics idea? Please raise your hands. Nice. So it's quite a few. I'm always amazed by how popular this topic is. I mean, we all know like why we need modular electronics. I mean, it's reconfigurable, it's reusable, it's less electronic waste. So I'm not going to talk about all of these. We all know about them. I'm going to take some inspiration from the software world, actually. And of course, every presentation needs this picture. So these two gentlemen, they changed history and changed our lives. However, they did not actually invent computers or programming languages or software, right? All they did was they provided us with platforms and tools so that we write our own software that runs on computers and smartphones. And when people like us, like me and you, when we wrote our software, it revolutionized the world in the last 3 decades. So software was really inaccessible, maybe back in the 60s and 70s. It was only for the elite, not anymore. Today, it's accessible by so many people. Unlike hardware, hardware is still only accessible by very few people. So imagine if many people have more access to hardware, if thousands of people can actually build and customize their hardware and basically take our jobs away. It would be fantastic. So why software is so accessible than hardware? One of the reasons that software is modular, and modular software is reusable. So you build something for one project, reuse it somewhere else. You basically just use Google and Stack Overflow and reuse code from the internet. Just kidding. But modular software is really much more useful on so many levels because since it's modular, you can divide it into chunks, you can give it to team members, you can put back the things together in the same project. Unlike hardware, in hardware, most probably you need to redo your design. You actually have to physically remanufacture the thing every time you need it. You can't reuse it. So the value of modularity is really undeniable. You can't argue with that. So what's Hexabit? They are small electronic boards, modules, they have specific sizes and shapes. They could come with hexagons or pentagons or triangles. And they're designed so that they can be combined together horizontally by soldering them side by side. And they would create larger contiguous electronic boards. These larger electronic boards could be flat or even curved. So these larger electronic boards, actually, they resemble and mimic custom-made PCBAs as much as possible, which is the end goal. They have a much similar form factor. They assembled horizontally. They are lightweight. They are small in size. They are rigid and reliable. They don't have wires and connectors and cables running around. So basically, the end goal is trying to mimic a custom-made PCBA. However, it's actually reconfigurable and reusable, because you can take all these chunks and replace them like they have problems, or upgrade your design, or disassemble it completely and reuse it in different applications. So each one of these modules has a single functionality by design. Say one would provide USB, one would provide a Bluetooth, one would be a motor driver, and you pick and choose from all these options. You combine them together in the shape and configuration you want, and then you get your larger configurable printed circuit board. So as you can see, the functionality usually lives on the top side of the module. On the bottom side, you have a small microcontroller that's actually providing all the flexibility and all the communication infrastructure, all the background and back-end activities that would actually make this possible and connect all these modules and reconfigure them. These modules, as you can see, they don't have connectors. I was targeting the lowest swap possible, so the minimum overhead, and remove the connectors and wires and cables and replace them with these edge PCB connectors that you can actually solder them together and get a contiguous board without any overhead or weight or holes. And the end goal would be something similar to this, or as seen on the other picture. So that's the concept. But how was my journey so far in the world of modular electronics? It wasn't straightforward. Actually, it was convoluted. So I was toying with modularity ideas, particularly for industry applications, as early as like 7 years ago. Spent a few years with different ideas and concepts and designs. You don't want to even see the old ones. I was never satisfied, gave up temporarily, just told myself this is like impossible idea to solve, and moved on to different stuff. Graduate school. In my PhD, I worked on optical arrays and pixelated optical elements, explored these low swap optical systems for multi-routers and drones. And then once, when I was done with this project, I started seeing similar modularity concepts everywhere, actually, especially in nature. I saw these similar concepts replicated everywhere, and thought myself, this is actually what I was looking for when I worked on modular electronics years ago, but I never realized it when I was doing the optics work. So I basically took the very basic modularity concepts, redesigned the software completely, redesigned the hardware to fit the new application, which is the modular electronics. And just got early prototypes earlier this year, just revealed like 3-4 months ago to some really close friends, and this is the first ever public talk about the project. So I'm excited about that. I'm going to talk a little bit about what's different between hexabits and everything else out there. In other words, I'm going to actually talk about what I have learned so far in my journey in modular electronics world through these ideas and prototypes. Some of the things I learned are actually counterintuitive, which is the reason they're good to share. So the first thing I learned that actually modularity is a really fundamental concept. It has, in fact, a mathematical solution in base. Specific geometric shapes like hexagons and pentagons and triangles, when put together in specific ratios, they create contiguous surfaces, whether flat or curved or spherical. And this concept is used extensively in nature. Like if you look at the insects, if you look at beehives, at molecular levels, at cellular structures, this concept is at the very basic of many natural designs. So taking these concept inspiration from both from nature and from math and applying them to electronics, we can build these modules with specific shapes and sizes and ratios, combine them together and create larger contiguous electronic boards. Why is that important? Because that's the form factor and shape and concept of a printed circuit board that we do these days. And if we want to actually replace it, we should try to mimic as much as possible, which brings us to the next point. So I learned that form factor is really important. Some of the reasons that many prototyping platforms, they don't actually end up in real life applications because they simply don't fit up there. I mean, like you can't really imagine taking a custom-made PCBA and replacing it with monster stack of boards and connectors and wires and all this overhead. I mean, it doesn't satisfy the weight or the size or the form factor or the integration. If our end goal is actually to replace custom-made PCBA, then we need to build our prototyping system to mimic custom-made PCBA. We don't make PCBAs vertically, we make them horizontally. That's why the default mode of integration in hexabits is going to the horizontal plane. You can still make stack-ups. I mean, you can still do whatever you want, but that's the default mode because the end goal is to try to replace and mimic these custom-made PCBAs and provide a really configurable and reusable version. The third point, I learned that actually peer-to-peer communication wins over bus architecture for the sake of modularity and scalability, which is really counterintuitive. When I started with the communication bus, with the electrical bus, because that's the first thing you think about when you start with the communication node. However, I quickly realized all electrical buses, they have topology limitations. You must connect things in specific topology and specific configuration. All of them, they have capacity limitations, whether it's capacitive or power or addressing. And these two limitations, they destroy the modularity and symmetricity concepts I wanted hexabits modules to have. So I decided to replace the bus architecture with a fully distributed and decentralized point-to-point communication, basically a wired mesh network. So taking ideas from wireless sensor worlds where they form all these complex wireless mesh networks and applying just basic principles to hexabits yielded really interesting results. For example, you can connect all these modules together. They would discover their surrounding. They would be able to communicate signals across the array, like from point A to point B, from point A to multiple destinations, or broadcasting signals, or that's all possible. The way this is implemented through these edge connectors. So the ones on the module edges are used for power. The one on the module sides are used for communication. So each one of these is dedicated to high-speed serial communication port. It's a UART port. When you use all these high-speed serial communication ports and couple them with DMAs, you can really do a lot of magic tricks, like moving things around without the CPU intervening. Some modules bypass message coming from the array from different destinations. You can do broadcast things from single point to multiple point to all of the communicated nodes. Even this would enable you to create a really complex control network, which is what you need here. I mean, there's not a lot of shared data and information between an LED and speaker and the motor drive and relay. I mean, you're mostly transferring control message and control signals. However, if you still want to do bulk data transfer, you can actually you can go and tailgate all of these ports and DMAs and create some kind of a pipeline that would like move data at much higher rates And even if you want to go much even higher, then you can create customized and specific ports. Let's say you have an FPGA and high-speed ADC. Then you only need this high bandwidth connection between these two modules. You don't need it across the array. Across the array, you have a control network that's much more manageable. And this shows the scalability of this concept. These are like 37 modules, 37 microcontrollers connected together with ease. So they would communicate, they would synchronize, they would play with each other nicely. And this is much easier to do with traditional concepts and different platforms and much like smaller form factor. So last point, I learned that we're already in the age of dust computing. I mean, we're used to the concept of smart motherboard and dumb peripherals and daughter boards. That probably 70s concept when computing was expensive. Today, computing is cheap, weak, is small, is low power. We can and we must embed it everywhere. So that's why all of Hexabit's modules, all the configurable ones, they have microcontrollers on small Cortex M0 microcontrollers. And you can think about this as like smart PCBs. You have these embedded logic blocks inside the PCBA that makes it configurable. So that's a form of this concept. The only downside here that really the embedded code development systems we have now really suck. So, I mean, although we already have like multiprocessor products and systems around, we're still designing the same old-fashioned where we go to each processor and design its own system, go the other one, and then manually do the communication and all of this synchronization. If dust computing and processing everywhere is the future, we really need a new way of designing embedded code where we design holistically for the entire system and still preserve the bare metal power of current systems. So I guess it's too long. It's too late. I'm talking about ditching custom hardware design for a group of hardware designers. However, the reason I'm here because actually you're the ones who can make it happen. The communities of hardware developers who can actually build these modules, their software drivers, find innovative applications, and build next-gen code development tools so that many people would find hardware design and customization much more accessible. So I have a preemptive answer for a question I've been asked a few times. So really, I mean, I've been to hear about Google's ARA project and other projects. Hopefully no one from ARA's team's here. I mean, I think really they did an amazing technical job. However, in my humble opinion, Google was solving the wrong problem. I think there is a huge distinction between user-facing and non-user-facing or back-end electronics. User-facing electronics like smartphones, smartwatches, they must be extremely streamlined to the user experience. So they must be the lightest, the smallest, the cheapest. They have beautiful design, and they really can't be modularized. Modularity adds overhead by definition. You can't argue with that. And people aren't going really to stop replacing their phones every 6 months because they're modular. I mean, people replace their phones because they like to show off and buy new stuff. So really the opportunity is in the back end. There's a huge opportunities in back-end electronics. Think about electronics inside your elevator, your washing machine, your car, your Roomba. People don't care about the electronics inside these devices. They're not constrained that much with form factor. They don't care what they look. They don't care if they're modular or not. However, they care that these things are customized. That's the promise of modular electronics, that you can actually customize to people much more easily. They also care that these things are reused later. I mean, if you're done with them, you can disassemble all these modules, use them in different products, different projects. So there is really a lot of modularization opportunities out there. But please, enough modular smartphones and smartwatches. So the current state of the project, um, that's, I would say, our hardware roadmap, a bit ambitious. So one of the things I learned that why many prototyping platforms don't end up in real life applications because of lack of options. I mean, we can't really be all designing with the same relay and the same LED and the same motor driver. I mean, that doesn't work. So that's why we have ambitious plans to have like 200, 300 options in the next few years. The core concept and ideas behind Hexabits makes it easier to build hardware and modules and software drivers than other systems and scale up. So you can see the green ones, they're already built, tested and implemented. The blue ones, they're being prototyped and designed, and all the gray ones, future. So a bit about software. It's designed on multiple layers. We're using STM32F0 microcontrollers. So you have the basic MCU hardware, the very basic hardware abstraction layers, and ARM SIMSYS drivers. On top of that, there's the embedded FreeRTOS, embedded RTOS system. There are some middleware applications for specific modules. On top of that, we built our own operating system, the BITS operating system, or BOS, that's actually managing all the background activities, the communications, the synchronization between modules, and some module drivers. And the last layer will have a command line interface and user applications. So basically, each one of these microcontrollers running multiple threads. You have the operating system. The BOS is managing threads that's going to the inter-array communication. Some threads are going to interface with the user through the CLI. Some threads are doing the actual function of the module, like the LED or the sound or whatever. And there is a user, there's a thread that you can write like simple applications, use like our APIs and functions, and don't go deep into the details. So this just resembles like a simple microcontroller that you're writing API applications in C. And you have also the CLI. So this really talks to different levels of people, whether you're on the advanced, you can take the hardware and throw our software away, or you're less experienced, you can start from the embedded RTOS, or you can go and just use the user applications, write simple C APIs, or you can just use the CLI, the command line interface, use any terminal, and send simple control commands. I'm going to skip over the first application video. So this video shows Hexabits concept. It's gonna work. Okay, and I have it on the drive for. Oh, maybe it was here. Let me find the video a bit. To figure out how to move this. Does it show up? Sorry. Oh, finally. So this is a relay hub project. It's actually using 12 AC relays that you can use to control AC load, let's say light bulbs and fans and whatever. And you have a DC-DC power supply that you can connect all of these modules together. And this would provide actually the supply for the microcontrollers here. Gonna see in this time lapse I was designing first the shape. I decided on this topology and shape. And then soldering, assembling the array. It's really easy soldering. You have large pads. Then once it's done, you run the CLI and ask these modules to explore their neighbors and build their communication and routing table and do all of these background activities. So these blinks, they resemble different actions like the module discovering its neighbors, assigning IDs, whatever ports need to be swapped or ports are normal, and then store all of these in the embedded flash and make it permanent. And now once it's done, somewhere here, you start getting response back from all the modules in the network. And you'll see how all the modules responded back. This is the routing table that defining the modules, their communication ports and locations, which ports are swapped, which ports are normal. And now you can actually use it for useful applications. So if you want to toggle all these relays, so you're actually broadcasting command to all of these modules and turning them on, only just to write this command. And these LEDs, they're connected directly to relay output, so actually the relay is turned on here. Now some of the mesh network magic, you can assign modules to different groups and then target only only specific groups. So I'm targeting only specific groups in the network or targeting all of them and sending the commands I want. Now, the best part, the promise of modular electronics, if you don't like the design, just disassemble it, make something else, use it in the same project, different projects, or put it back on the shelf. Let's see, I think we're done here. Let's go back to this guy. Some issues. Yeah. So final words. If you like to try the future, just shoot me an email. This is still very experimental. It's really early bird. What's next for Hexabits? Of course, many more modules. There's enough of them, never enough of them. I'm also building a team and looking for seed funding to try to bring this to market. So if you know any really good investors or funding sources, I would appreciate the introduction. And thank you all for being here.